The long-term fate of a star depends on its mass. We've seen that objects less than 8% of the mass of the Sun never attain the high temperatures required for hydrogen fusion. Those are the brown dwarfs. More massive objects do ignite hydrogen fusion and become stars. Up to about 8 solar masses, they end up sloughing off enough material during the giant phases that their cores can be supported by electron degeneracy pressure, so they become white dwarfs. A star that's initially heavier than 8 solar masses ends up with a core exceeding 1.4, the Chandrasekhar mass. The core collapses, forming a neutron star. But neutron stars have a maximum mass too, above which gravity overwhelms even the strong nuclear force. We don't know exactly what that upper limit is, but it's probably not much higher than 2 solar masses. So truly gargantuan stars, initially more than 20 solar masses, probably collapse into black holes. I've already spoken about one way neutron stars announce themselves to astronomers, as radio pulsars. Another way is through X-rays. In the early days of X-ray astronomy, in the 1970s, some of the strongest sources were found to be binary stars. Or at least, Doppler spectroscopy revealed one star that was being pulled around by a massive companion, but there was no light from any second star, just X-rays. To understand the X-rays, imagine the following scene. An ordinary star and a neutron star are in a tight orbit. The normal star swells up into a giant star and gets distorted by the strong tidal forces from the neutron star until it violates the Roche limit. Material from its outer layers spills out, but it can't fall directly onto the neutron star. It has too much angular momentum. So it swirls around the neutron star, forming a vortex, like water draining down a bathtub. In this context, the vortex is called an accretion disk. Gradually, the material loses angular momentum and falls toward the neutron star, releasing a lot of gravitational potential energy along the way. The gas heats up to tens of millions of degrees and glows with X-rays. We can calculate how much energy is released by following the progress of a small amount of gas with mass m as it spirals down the drain. The spiraling is a slow process, so at any moment the gas follows a nearly circular orbit. If the gas starts at some large distance, where the orbital energy is practically zero, and descends down to the neutron star radius, r, the energy released is given by the usual formula for orbital energy, g times big M times little m over 2r, where big M is the mass of the neutron star. Is that a lot of energy? It's hard to say without making a comparison. One way is to divide the energy released by little m(c squared), the maximum possible energy that could ever be extracted from a substance of mass m. In this sense, delta E over mc squared represents the efficiency with which the mass of some fuel is being released as energy. Burning kerosene releases 46 megajoules per kilogram. If we divide 46 megajoules by 1 kilogram times c squared, we get 5 times 10 to the minus 10, half of a billionth. That's a typical value for a chemical reaction. Fusing hydrogen into helium releases 7 mega-electron volts per nucleon. And if we divide that by 1 proton mass times c squared, we get 0.0075, which confirms what we already knew. Nuclear fusion is vastly more efficient than chemical combustion. Well, we can consider an accretion disk as a sort of gravitational combustion. It converts falling mass into intense radiation. If we divide the energy released by mc squared, we get an efficiency of g times big M over 2rc squared. Plugging in typical neutron star parameters, a mass of 1.5 suns and a radius of 10 kilometers, the efficiency comes out to be 1/10. That is a lot. Gravitational accretion outdoes nuclear fusion by more than an order of magnitude. It makes me wonder if our descendants in the distant future, the really distant future, will outgrow nuclear fusion as a way to power their civilization. Instead, they'll tow in a neutron star from some other place in the galaxy and throw things at it and capture the energy that shines away from the accretion disk. Accretion disks are widespread throughout astrophysics. You find them around not just neutron stars, but also white dwarfs and black holes. Even a normal star can accrete mass from a companion, although it doesn't release nearly as much energy because the material doesn't have as far to fall. For normal stars and white dwarfs, the accretion disk glows in the visible and ultraviolet range. For neutron stars and black holes, it's X-rays. By the way, how can you tell if it's a neutron star or a black hole? The usual way to distinguish is by mass. If we can sense the motion of the normal star through the Doppler effect, we can measure the minimum mass of the accreting object. If it comes out to be more than, say, 3 solar masses, it's probably not a neutron star. That's above the maximum mass that could be supported by the strong nuclear force. A few years ago, if you'd asked me, what's the best evidence that black holes really exist? I would have pointed to X-ray sources like Cygnus X1, where we see a normal star being gobbled up by an object packing 15 solar masses. I would also have pointed to the stars whirling around the center of our galaxy, which we discussed in Lecture 7. But these days, we have even more direct evidence for black holes from a truly magnificent experiment. I'm talking about the detection of gravitational waves from merging pairs of black holes. Until the early 20th century, gravity was conceived as a force that one mass exerts on another. A mass can just reach across space and pull on other masses. Einstein taught us it's not like that. Masses don't directly pull on each other. Instead, a mass distorts the surrounding space. It curves it, the way that a bowling ball curves the surface of a trampoline. Then, other masses follow the curvature of space instead of just coasting by. If you roll a marble on the trampoline, it curves around the bowling ball. From high above, it might look like the bowling ball is pulling on the marble, but the connection is indirect. Paraphrasing the physicist John Wheeler, mass tells space how to curve, and space tells mass how to move. One implication is that gravity doesn't act instantly. If a mass changes location, there's a slight delay as the stretching of space is transmitted outward. That allows for the possibility of gravitational waves. It might help to switch analogies and think about a case where the delay is obvious. Say you're in a large swimming pool. If someone does a cannonball dive on the other side of the pool, it takes a while for the waves to reach you. Likewise, when black holes crash into each other, there's a delay before the resulting distortions in space reach us. But while a water wave might travel a few meters per second, gravitational waves travel at 300 million meters per second, same speed as light. Another difference is what happens when the wave reaches you. If I'm in the water and a wave reaches me, I bob up and down. But if I'm in space and a gravitational wave reaches me, I get stretched. First vertically, then horizontally, then back to vertical, and so on. I feel oscillating tidal forces. One way to visualize the effect is to imagine a series of circular rings arranged to make a cylinder. Then send in a gravitational wave along the axis of the cylinder. Each ring gets alternately stretched one way then the other. The result is a traveling pattern of distortions. In real life, the stretching motion is unimaginably small. even the strongest gravitational waves that pass through the Earth stretch things by only a few parts in 10 to the 21. That is, my height in meters changes only in the 21st decimal place. When I first learned about this incredible weakness of gravitational waves, I thought, okay, I guess we can forget about ever detecting those. It's totally impossible. And yet it has been done by a large team led by scientists at MIT and Caltech. So how did they achieve the impossible? The clue is in the name of their facility, the Laser Interferometric Gravitational Wave Observatory, or LIGO. Do you remember interferometry from our lecture on radio telescopes? The idea there was to take advantage of the wave nature of photons to sense tiny differences in direction that the waves are coming from. LIGO takes advantage of the wave nature of photons to sense the tiny changes in length induced by a gravitational wave. It's sneaky. They use electromagnetic waves from a laser to detect gravitational waves. They built tunnels in two perpendicular directions. Let's call them north and west, although the actual orientation doesn't matter. A gravitational wave changes the relative lengths of the tunnels. One gets stretched while the other gets scrunched, and vice versa. So the goal is to continuously monitor the relative lengths of the tunnels. And the way it's done is to send laser light through a beam splitter, essentially a half-silvered mirror that reflects half the light to the west and transmits the other half north. At the end of each tunnel is a highly reflective mirror which bounces the light back to the beam splitter. And from there, the light either goes back toward the laser or bounces to a photodetector. If the two laser beams arrive at the detector in phase, that is, if each crest arriving from the west is met by a crest arriving from the north, then the beams interfere constructively. The combined light has a higher amplitude than either beam separately, and the detector registers a large signal. If, on the other hand, the two optical paths differ by half of a wavelength, then the beams interfere destructively. Each crest from the west is met by a trough from the north, so the signals cancel out, and no light gets to the detector. The experimenters arrange for destructive interference, and then they work as hard as they can to maintain that condition, keeping all the equipment stable. They call this condition fringe lock, the fringe being the dark fringe in the interference pattern formed by the two laser beams. Then a gravitational wave comes through, stretching one tunnel and squishing the other back and forth and back and forth. This breaks the fringe lock. Some light reaches the detector, oscillating in intensity at the same frequency as the incoming gravitational wave. So that's the game. Arrange for destructive interference, hold everything fixed, and then hope that two black holes collided in the remote past and their gravitational waves are about to reach the Earth and wash over the detector, causing a flicker of laser light. This is not easy. As I said earlier, the stretching effect is minuscule. The strength of a gravitational wave is quantified by its strain, defined as the fractional change in length it produces, delta L over L, which, as I mentioned before, is, at best, 1 part in 10 to the 21st power. One thing that helps is to make the tunnels very long, increase L as much as possible so that delta L is also larger and easier to detect. The LIGO tunnels are 4 kilometers long. In addition, there are extra mirrors that bounce the light back and forth hundreds of times, which has the same effect as lengthening the tunnels. Another challenge is making sure the mirrors are kept isolated from external vibrations. The slightest tremor from a distant earthquake or a passing truck or even sound waves would knock the mirrors out of alignment. So the experimenters pump all the air out of the tunnels and use the world's best shock absorbers. And even then, even in fringe lock, the detector's never totally dark. There are always some vibrations unrelated to gravitational waves that simply can't be filtered out. So what do? You build two interferometers at different sites. One is in Hanford, Washington. The other is 3,000 kilometers away in Livingston, Louisiana. The idea is that the random fluctuations will be different at the two sites. You only get excited when you see the same signal at both locations at the same time, or at least nearly the same time. Depending on where the wave is coming from, it'll arrive at one site earlier than the other one, but still within 10 milliseconds, the time it takes to travel 3,000 kilometers at the speed of light. In fact, you can use the measured delay to help figure out where the wave is coming from, although not very well. You can't pinpoint the location of the source on the sky. By measuring the delay, you can only restrict the possibilities to a certain circle on the sky. So what do? You convince your friends in Europe to build an interferometer too. LIGO works in conjunction with a facility called Virgo in Italy. With 3 detectors, you can measure 2 delays. The signal hits Virgo first, then Livingston, then Hanford, and that's enough to triangulate the position of the source on the sky. Let's spend some time examining the data from the historic first detection of gravitational waves in September 2015. This chart shows the signal measured at the Hanford site. The horizontal axis is time. Notice the whole chart spans only 1/5 of a second. The vertical axis is the strain, expressed as a multiple of 10 to the minus 21. Before about 0.33 seconds, the data look like random noise. Then an oscillation starts to build, getting stronger and more rapid, and then disappears at 0.43 seconds. That signal represents the ripples of gravitational waves that arrived at the Milky Way from a remote galaxy where billions of years ago, a pair of black holes spiraled together. Anyone in that galaxy who witnessed the event up close would be laughing at my portrayal of gravitational waves as weak. Up close, space was churning furiously as the black holes orbited around one another. The resulting gravitational waves carried energy away from the system at the expense of the orbital energy. That made the orbit shrink, causing the black holes to speed up, which increased the rate of energy loss still further. This positive feedback loop explains the quickening oscillations in the Hanford signal. Then the two event horizons merged. The two black holes became one, and the waves stopped. The data from Livingston tell the same story. The signal is consistent with the Hanford data after accounting for the different locations and orientations of the two interferometers. Another way of viewing the data is a frequency-time diagram. The horizontal axis is still time, but now the strain is indicated by color, and the vertical axis is frequency, the rate of oscillations at a given time. The colored stripe starts out horizontal and then curves up to the right, which tells us that as time progressed, the frequency increased. The oscillations got faster as the black holes approached each other, until in the last fraction of a second, the waves reached a crescendo and made a chirp that was heard billions of light years away, with the right equipment. And when I say heard, I'm using a pretty good analogy. The frequency of the gravitational waves in that last fraction of a second ranged from 50 to 300 hertz. For sound waves, that's within the audible range of frequencies. This coincidence makes it impossible to resist converting the gravitational waveform into an audio waveform. That is, take the mathematical function describing the oscillating amplitude of the gravitational wave and use that function to drive a loudspeaker. Here's what it sounds like. That's the sound of two black holes merging. It's easier to hear if we scale up the frequencies a little. Based on the maximum frequency of the signal, we can calculate the masses of the two black holes. To calculate them accurately requires the machinery of general relativity, but we can get an approximation with the help of our old friend, Kepler's third law. Kepler's third law allows us to calculate the total mass of a binary if we know both the orbital period and the orbital separation. To keep things simple, let's consider a pair of black holes with the same mass on a circular orbit with a period p and a separation a. The data show that the gravitational wave rose in frequency from 50 to 300 Hertz. That corresponds to wave periods ranging from 1/50th to 1/300th of a second. In our scenario, the wave period is equal to 1/2 of the orbital period. That's because after half an orbit, the black holes switch places, and since they're identical, the system looks the same again. So the pattern of gravitational waves must repeat every half of an orbital period. We conclude that the orbital period shrunk to a minimum of 1/150th of a second. And what about the orbital separation? We can't just read that off the chart. But we can reason that the period was shortest just before the final merger, when the two event horizons started touching each other. At that moment, A was equal to about twice the Schwarzschild radius. And now we can apply Kepler's third law. The total mass, 2m, equals 4 pi squared over g times a cubed over p squared. For a, we insert 2 times 2gm over c squared. Now m appears on both sides of the equation. We solve for m, and then run the numbers, using p equals 1/150th of a second. The mass, m, comes out to be 38 solar masses. This agrees pretty well with the more sophisticated analysis by the LIGO team, which found the two black hole masses to be 36 and 29 solar masses. The other key piece of information from the chart is the maximum strain, 10 to the minus 21. We can use that to determine the distance to the galaxy where the merger took place. But first, we need a formula telling us how the strain decreases with distance. To determine distances, we often rely on the flux-luminosity relation, F equals L over 4 pi d squared. We derived that a long time ago, based on the conservation of energy. All the power from the source gets spread out over a giant sphere of surface area 4 pi d squared. The same is true of gravitational waves. But there's a twist. LIGO is not a flux detector. The response of the interferometer is not based on the flux of energy carried by the waves. It responds to the oscillations themselves. It directly measures the wave amplitude, the strain. It's like the difference between detecting ocean waves by tracking the rise and fall of a floating buoy, that would be an amplitude-based method, or detecting ocean waves by letting them crash into a wall and seeing how much the wall heats up. That would be a flux-based method. Since amplitude varies as the square root of flux, the amplitude of a wave goes like 1 over distance, not distance squared. So we expect the formula for the strain of a gravitational wave to be something divided by d. And what is that something? What should go in the numerator? That's a job for a general relativist, but we can make an educated guess. Gravitational waves are produced whenever a mass is shaking around, so we might expect the amplitude to depend on the mass and how fast it's shaking. When black holes merge, when their event horizons touch, how fast are they moving? Turns out they're moving close to the speed of light, c. If you don't believe me, try setting the centripetal force on one of the black holes equal to the gravitational attraction to the other one. You'll find the speed to be about 35% of the speed of light. So in the strain formula, we expect the numerator to depend on m and c. And because this is gravity, g should also make an appearance. Now let's think about the units. The formula we're seeking is for strain, which is unitless. It's a fractional change in length. And the denominator is distance. So the numerator must also be a distance. And how do we build a quantity with units of distance from m, c, and g? We already know the answer. It's gm over c squared. It's proportional to the Schwarzschild radius, which we know has units of distance. In short, we expect the strain to be on the order of gm over c squared divided by d. We can use this fact to calculate the distance the gravitational waves traveled before they reached the LIGO detectors in September of 2015. We solve for d, insert 10 to the minus 21 for the strain, and 39 solar masses for m. That gives a distance of 1.8 billion parsecs. A more accurate analysis based on general relativity gives 0.4 billion parsecs. So despite the questionable application of non-relativistic formulas to black holes moving at the speed of light, we did get the right order of magnitude. A billion parsecs is a long way away, which tells us two things. One, mergers between giant black holes must be rare if the first one we found was so far away. The current best estimate is that a galaxy like the Milky Way hosts one of these events every 100 million years or so. The second thing is that the total energy released in gravitational waves must be tremendous to be detectable at such a distance. We can calculate that energy released by asking how much the orbital energy decreases when the black holes start in some wide orbit and spiral inward until their event horizons touch. The answer is gm squared over 2a, where a, the orbital separation, is twice the Schwarzschild radius. We can simplify that, and when the dust settles, the answer is 1/8 mc squared. The efficiency, as I defined earlier in the lecture, is 1/8. If we plug in 39 solar masses, the delta E comes out to be about 10 to the 48 joules. That's a lot of joules. It's 100 times more energy than a core collapse supernova, which seemed so impressive just one lecture ago. And almost all of that energy is released within 1/10 of a second. So for that brief interval, the luminosity is of order 10 to the 49 watts. To put that into perspective, we can also express it as 10 to the 23 times the sun's luminosity, or 10 to the 12 times the luminosity of all the stars in the Milky Way. Those two merging black holes were, for a brief moment, emitting more power than 1 trillion galaxies. These are truly stupendous events. You might be wondering, where did these black holes come from? What brought them so close together that they ended up merging? Those are still open questions. It might have been a binary star system where both stars were massive enough to collapse into black holes. Or maybe two black holes in a dense star cluster had a chance encounter. As if colliding black holes weren't enough, another momentous discovery came in August of 2017, when LIGO and Virgo detected the gravitational waves from a pair of merging neutron stars. In that case, the frequency time diagram shows a longer signal lasting 30 seconds instead of just a fraction of a second. That's because neutron stars are only around 1.5 solar masses instead of 40, and it takes longer for them to radiate away all their orbital energy. This discovery was front-page news, not only because neutron stars are awesome, but also because afterward, astronomers detected the afterglow of the merger, a new source of light, X-rays, and radio waves emanating from that distant galaxy. You see, Colliding black holes produce no electromagnetic radiation. They're black. But colliding neutron stars produce a fireball. And the observations of the afterglow confirmed the predicted characteristics of the fireball. The fireball models also predict that the conditions are so extreme that a series of exotic nuclear reactions takes place. Reactions that require a massive dose of neutrons, forging many of the heaviest elements in the periodic table, like bismuth, thorium, uranium, and the biggest crowd pleaser, gold. It's now thought that almost all the gold in the universe is thrown off like sparks from colliding neutron stars. Each collision produces a few Earth masses of gold. All of these jaw-dropping scientific and technological marvels earned the leaders of the LIGO project, Rainer Weiss, Kip Thorne, and Barry Barish, the Nobel Prize in Physics in 2017. It was probably the most easily predicted Nobel Prize of all time. They and the teams they led gave birth to a whole new branch of astronomy. For centuries, astronomers relied almost exclusively on electromagnetic waves to learn about the universe. Now we can start using gravitational waves too. If you're ever feeling down, thinking about all the failings of human civilization, remember the story of gravitational waves. You have to admit, at our best, humans can be ingenious, both for dreaming up wild theories of the universe and then designing experiments to test them.